So today, inshallah, Bismillah ar-Rahman, today we'll start chapter 9. And as we have finished all the layers, we discussed the whole stack, including the physical layer as well. This chapter and the next chapter we'll talk about standards. So we are still in the data link and physical layer, and today we are going to discuss one of the most common, or maybe the predominant standards in the data link layer and the physical layer. So Ethernet tries to standardize the protocols in the local area networks, including the data link layer and the physical layer. Ethernet is just a family of multiple protocols and standards, including the logical link control, the MAC layer, and the physical layer. So this is where the Ethernet standards represent in the TCP/IP stack. So it includes the logical link control, MAC, and physical layer. If you remember, I mentioned before that logical link control is a separate standard. So what Ethernet does is that it refers to this standard as the standard for the logical link control sublayer. So Ethernet itself defines all the details in 802.3 in the MAC layer and the data link layer. But the logical link control, this has been standardized before in early days, and Ethernet just refers to it as this is the part of the standard related to logical link control, because it doesn't change for UTP versus fiber optics versus any other physical medium. So 802.3 is basically what we will discuss in this chapter, including the mechanisms in 802.3 for to support MAC layer functionality and physical layer functionality. For MAC layer, we talked about multi-access and physical addressing and so on and so forth. And then for physical layer, we talked about encoding and signaling and so on.
Sorry, I have a question.
Sure.
Now, Ethernet, it refers to the wire?
Yes, wired, yes. Ethernet is the standards for the wired networks.
Wired.
For wired networks, not for wireless.
I thought the kind of, type of wire is Ethernet. Is there?
No. There is no such type of wire as Ethernet wire, no.
Okay.
Ethernet is the name of the family of standards that govern the functionality of the wired networks in specifically in layer 2 and layer 1. Okay, in data link layer and physical layer.
And by physical layer, it's MAC layer. It's MAC sublayer.
Doctor, and again, is in data link, there is also MAC layer.
Right. Yeah, so the MAC layer is the part that changes because of the fact that we are talking here about wired. Okay. So if you're talking about wireless, it's totally different standards, which is 802.11.
Yes.
This is 802.3. Yes, that covers MAC and physical layer. 802.11 covers it's the corresponding standards, just as for Ethernet, but for wireless. Okay, and both of them, as this slide here tries to explain, that all the standards in the data link layer and physical layer, they all refer to the logical link control, which is 802.2, because it's as we said before, it's medium independent. Okay, so you don't have to change that part for every single standards that we talk about. Okay, so Ethernet, talking ring, FDDIs for fiber optics, all these are names of standards that deal with different types of medium. Okay? And all of them, they refer to the same logical link control sublayer, which does not change by the change of the medium. Also, the logical link control acts as an interface to the upper layer. As we said, fundamentally, all the layers are isolated from each other. So the logical link control provides the interface between the upper layers and the MAC layer and physical layer. So in that case, whether you're talking about IPX or IP or AppleTalk or whatever protocol that you're using in the network layer, you can go to the physical layer and data link layer through logical link control. This is the first sublayer that's responsible for framing and error correction or error detection, right? So these are the two functionalities for the logical link control. Just the initial framing and error detection, that's all. Okay, and in addition to this, it actually provides the interface to the higher layers, and this is the first thing that creates the frame to send to the physical layer. As this illustrates here, this is the legacy technology, which means that all these technologies or all these standards that have started, they are not existing anymore. They are obsolete and nobody uses them. Okay. So this is the most important characteristic of the logical link control, is that it's independent of the physical equipment or the physical medium. So the first sublayer that's fundamentally different for the case of Ethernet is the MAC layer, or the medium access control sublayer. So the medium access control sublayer deals with the protocols that host multiple nodes to access a shared medium or to access a physical medium. In our case now, the physical medium is wired. So if you're talking about wireless, do not mention Ethernet for the case of wireless at all. This is wrong. So Ethernet is only for wired systems, only for wired networks. You can use Ethernet for coaxial. That's possible, or UTP. Okay, for coaxial, as we said, we will use the T connectors or for the case of UTP, we use hubs or switches or something like this. Of course, the MAC layer is responsible for two things: the physical addressing, especially if we're talking about multiple access, and the media access control. When do I have to access the network? The Ethernet uses the concept of Cmpe CD. We explained that concept briefly before. For Cmpe CD, or carrier sense multiple access with collision detection. So for the case of wired, it's always possible to detect collision. Why? Because the signal itself, when it travels through the wire, the energy remains almost constant. Okay? Versus if you send the signal over the air, it loses a huge amount of its power as it propagates through the air. So at any point in time on the wire, if you have two nodes are trying to send on the wire, you see that the power level on this wire increases significantly, right? Whereas for wireless, it's very hard. When I listen to the air, I don't really know whether there is one node or two nodes are sending. I can measure if anyone is sending. If the power level is higher than certain limits, so I can say, okay, there's somebody sending, so I should stop. Okay, it's like the roundabout is busy now, so I should wait until it gets free. But I wouldn't be able to tell whether there's 1, 2, 3 nodes. I don't know. Okay, so a collision happens if there are more than one node are trying to access the medium. So 2 or above, this is collision. But in wireless, it's very hard to detect that situation in which case we use, instead of CDE, we use CA, or collision avoidance. We don't detect collision, but we try to avoid it. And we use different techniques to do that, which we don't have to go through. So SESMA CD basically talks about the fact that, like I have to listen whether there's someone sending on the line, and if zero nodes are sending, then I can send, okay? But when I send, I also listen to the medium. After sending, I still listen to the medium. So sensing is continuous, because when I send, I need to make sure that while I'm sending, I'm the only one who's sending, because if two nodes are sending, then the power level increases more than the power level that I use to send the signal, in which case I detect that there is a collision. And when I detect that there is a collision, then I have to inform everyone that there is a collision. So in that case, we all stop until everything clears from the channel, and then we keep sending again, or we keep sensing again. So this is the basic concept of SESMA CD. So the Ethernet is implemented in terms of, as we said before, in terms of hardware and software. So we have this, what we call the network interface card. You don't have the luxury, or you didn't have the chance to see this card, because nowadays this card is actually built in all the motherboards and all the laptops or workstations that we have nowadays. So in earlier years, the NIC card used to be like a separate card that you connect, because in the past there was an option whether you want to hook up your PC to the network or not. Of course, nowadays people realize that this is not an option, so it's a must. So this is the basic necessity of all the PCs and laptops that we have. So that forces people to actually integrate the NIC card as part of any motherboard or any laptop that we use. So this NIC card implements the protocols and the data link layer, including logical link control and 802.3 or Ethernet. It has the connector here to connect UTP or coaxial. Of course, coaxial is obsolete now. Nobody is using that anymore. There is, of course, the hardware that implements the physical layer in terms of encoding and signaling and dealing with analog signal and so on and so forth. This is purely hardware. When it comes to MAC layer and logical link control, this is done mixed between hardware and software. We have mentioned that before. So there is an embedded software that runs on this NIC card to perform the MAC functionality and the logical link control in terms of error detection and so on and so forth. Most common layer 2 NIC cards are Ethernet and 802.11. This is a fact. The bandwidth of the NIC card is measured using the theoretical data rates or the physical layer bandwidth. So when we say this is 10 or 100, this means that this NIC card can use one of these two speeds. So the maximum speed that this NIC card can use is 100 megabits per second as a theoretical bandwidth. But this card can work as well on a lower speed. When does this happen? If the card is trying to connect to any other device that uses only 10 megabits per second, then it lowers its own speed to 10 megabits per second to be able to talk to each other. This is part of the protocol. If you are talking the same protocol, then you can communicate. Otherwise, I cannot send you with the speed 100 megabits per second, and you only support 10 megabits per second. In that case, you will not be able to cope with the speed that I'm sending. So this means that the NIC card can use either speeds to communicate. But of course, the actual throughput is a lot less than these speeds we have discussed before. So this is how you connect. So each NIC card will get connected to the hub using the UTP cable or the switch. So this can be a hub or a switch, and there is a fundamental difference between the two, which we have hinted before, and we'll talk about in more details in this chapter. If we connect the multiple nodes, including servers or PCs or laptops or something, through the hub, then we create a logical topology of a shared medium. So this is a shared medium between all these PCs and laptops, which means that in that case, if two nodes are trying to send at the same time, the collision will happen. This is not the case if you switch this hub to a switch, as we see. Okay, so another important aspect of the MAC layer is what we call the physical address or the MAC address. So MAC address or physical address is the name for the same thing. And the MAC address in that case is actually is 6 bytes, which is larger in size compared to IP. So the IP used to be only 4 bytes. This one uses 6 bytes. And these 6 bytes are divided into 2 parts. So the structure of the MAC layer address is totally different. As we have discussed, the IP address structure is based on the subnetting and how you divide the network into subnets, right? Here, the structure is not related to that. It doesn't have anything to do with the way you divide the network, because we're talking about the same LAN. So here, the Ethernet is for one LAN, and you don't divide the LAN into subnets. Yes. So the structure here is based on the fact that we want to uniquely identify this card to have physical communication. So in that case, the structure is divided into 2 parts. One is the organizational unique identifier, and this refers to the vendor ID. Mm-hmm. So this part is assigned, as we will see, not by the manufacturer. This is defined by IEEE, the authority that identifies the vendor identification for all the vendors across the world. If you can make this part unique, then you leave it up to the vendor then to assign the other part. So the other part is assigned internally by the vendor, because of course each vendor manufactures multiple cards, multiple types of cards, right? For Ethernet, for wireless, for whatever. So in that case, they have 3 more bytes to identify which card they want to manufacture. And actually each card has to have, even within Ethernet, if they want to manufacture cards for Ethernet, each card should have a unique identifier in such a way that that you can physically identify this address. So the MAC address gets actually hard-coded into the NIC card. So it gets permanently stored inside the hardware in the EEPROM of the NIC card. So it's permanent. It gets assigned permanently, and it doesn't change. If you want to change it, then the manufacturer is the only one who can change it. So every Ethernet NIC card has a unique permanent MAC address. You cannot change it. It's not configurable like the case of IP. It's not assigned by DHCP. Nothing of this. It's permanently assigned. Okay, and it doesn't change at all. Okay.
So, Doctor, one card has 2 IDs?
No. It's the same address but has 2 parts. Part identifies the manufacturer, so So if I see this part, I should be able to know whether this is manufactured by, for example, Cisco or D-Link or whatever. Okay? And then the other part can identify the card itself internally. So, which means that two manufacturers can manufacture a card with the same card identifier. That's okay. You will never have any collision or any match between the physical address that gets assigned by one vendor and the other. Why? Because the vendor ID is different. And this is assigned by a centralized authority, which in that case is the IEEE. So MAC addresses are 48 bits, and that's why we don't have any problem or shortage in MAC address, at least until today. Where, so you have trillions of addresses for MAC addresses that we don't have the same issue like IP, at least until today. And this is built or burned in address in the ROM of the NIC card, and then it gets initialized or updated in the RAM once you start your PC.
Yes.
So once you start your PC, it gets read from the ROM or EEPROM of the NIC card, and then it gets loaded to the memory so that you can use it for communication. So the organizational unique identifier, it gets assigned by IEEE, and then you have three other bytes, or in that case, three bytes. 3 times 8 is 24, so that gives you 6 hexadecimal digits. 6 hexadecimal digits, because each digit is 4 bits for the case of hexadecimal. So that identifies the vendor specific ID for that particular card, for that particular NIC card. So the Ethernet protocol uses these MAC addresses to identify the source and the destination. So they get inserted into that these two fields in the frame. Okay, so this is the destination physical address and source physical address, and each one of these is actually 6 bytes or 48 bits. Okay. So whenever a computer sends an Ethernet frame, it includes both MAC addresses, and since this is used for device-to-device communication, as we have mentioned before, for each hub, you have to change the MAC address. So from one device to another, the device has to read the frame and then regenerate the frame again when it sends to the other device with different MAC addresses, both source and the destination. So these are the two parts of the physical address, and as we can see, you have 6 digits, 6 hexadecimal digits. So here we don't use the dot decimal notation. Remember in IP, we used to use decimal notation. More than 32-bit, it starts to be hard to use dot decimal notation. So here we use, similar to IP version 6, if you remember, we used hexadecimal digits because the hexadecimal digits, they can summarize 4 binary bits in one digit. So that helps us to represent it in a short form, relatively speaking. So we use 6 hexadecimal digits for the OUI, or the organizational unit unique identifier, and then another 6 hexadecimal digits to uniquely identify the card ID. Okay. So fundamental difference for the case of MAC address. MAC address is flat in the sense that it does not give me any structure or any idea how my network is divided or how my network is subnetted, and it shouldn't actually. It's not meant for this. But this is one of the fundamental differences between IP and the MAC address. IP used to give us some kind of structure, We know that this IP is divided as follows. You have one big network part, and then the sub-network part, and then the host part, and so on. Okay, so that gives you an idea how to find the host, and that's useful because this helps routers to send it first to the country where this host is, and then from the country to the tier 2 operator where this host is, and then from tier 2 to tier 3, and then from tier 3 to the host. So it gives you some idea how to find the host on the internet. The MAC address doesn't do that, and it's not the responsibility of the MAC layer to know the physical address of another PC in China. It's not the responsibility of the MAC layer. The IP will do that. So once it reaches to the ultimate network or the LAN where this host is, then you go layer 2 and then you use the physical address. So the physical address itself has a flat structure. It doesn't have any structure that identifies how to send the frame. Okay. So if we were to bring all together, so Ethernet frames use the physical address, and physical addresses are flat. They are not structured, but they give us the physical address of the host that's connected on the same LAN where we share a physical medium together. Also, this uses Cmpe CD for carrier sense multiple access and collision detection. So in that case, if we bring all together and we have all this figure, so LANs are usually connected through multiple devices, whether it's switch or hub. Once you connect to a router, we identify this as a LAN on its own. So if the LAN has a hub, okay, so that reflects to a multi-axis mechanism, or as a logical topology, it represents multiple axis, in which case we have multiple nodes connected to the same shared medium. In that case, we need to use physical addresses, okay, to identify which node we're trying to send to, and we need to use Cmpe CD to control the access to the mediums. That's very important, right? It becomes fundamental in that case. If we, as we will see later, if we switch these hubs with a switch, then in that case we still need physical address, okay? But we don't have to use Cmpe CD. Cmpe CD disappears because we don't have any shared medium in that case. But we still need physical address to know where we want to send. The physical addresses are going to be used by the switch in that case to send the frame on the port where the host is connected to. Whereas for the shared medium, everybody's going to listen to it. Everyone is going to get a copy of the same frame, and then it checks and matches the physical address against the physical address in the frame to know whether it should consume that frame or just ignore it. For the case of router-to-router communication, right? In that case, we commonly use serial PPP. Okay, so in that case, it's outside of the domain of Ethernet. Okay, even though we're talking about a wired medium, but we don't have any Ethernet in that case. We use serial PPP as a protocol. We did not discuss this. We did not discuss the protocol in details. But we know that conceptually, for serial PPP, we don't have to use physical addresses. We don't have to use Cmpe CD. We don't have to use any of this. Any frames that you send from one end, it will reach to the other end. That's it. Okay? So this is bringing everything together. So Ethernet talks about multi-axis, if we are talking about an Ethernet hub here. And then talking about multi-axis, we have multiple concepts that we need to understand. which we have discussed before. So, the first thing we need to know is that if this node wants to send to this node, for example, when it sends on a shared medium, which in that case is represented using the hub, so the signal, the analog signal, will go through the shared medium, and everyone will be able to absorb it. Absorb it is different from consume it. So when I absorb it, this means that I will have to detect the analog signal. I will have to convert it to digital. This is physical layer part, and then in the data link layer part, I have to read the physical address only, read the header only. Okay. And then match the physical address in this header. Again, it's my physical address. If it matches, then and only then I copy the contents in my buffer. Otherwise, I just ignore it. So this shared medium is implemented using a hub or using the T connectors, which we don't use anymore. So this is in the case of coaxial. Okay. This is called shared bus. They call it shared bus, although bus is now commonly used for computer architectures when we talk about buses and tech. Yeah, but this used to be called bus, coaxial. Okay. So when information is transmitted, the PC will put the destination address that it wants to communicate to, and in that case, for the shared multi-access, everyone will read it, and then this address is the most important part where I know whether I should consume it or just ignore it. So unless we are running a protocol analyzer program like such as Ethereal, so if you're trying to receive a proper communication from someone, then you filter all the incoming frames based on your physical address. So if the destination physical address matches yours, then and only then you consume it. Programs like Ethereal, these are like Wireshark. They listen to all the incoming frames, and they consume it all. Why? Because they want to. Because these types of programs, they consume all the packets because they monitor the traffic on the shared medium. Okay, it's their responsibility is to monitor. So they want to read and consume all the packets and give you information about these packets. So in that case, it consumes all the packets on the shared medium. This can also be, there is a corresponding, so this is for Ethernet, but there are some programs similar to that on Wi-Fi and so on. Yeah.
So these type of programs called analyzers?
They call protocol analyzers. Sometimes we call them sniffers. Yeah, so yes, or monitoring software, something like that. But these are useful as you have gone through the lab. These are very useful to give us some idea about the traffic that is flowing through the network. Okay. So what happens if multiple computers are trying to send at the same time? Collision will happen. When the collision happens, the fundamental thing we need to know is that we cannot extract any signal from the other. Both frames are wasted. Okay, there's no possibility for us to recover from any collision. In reality, this means that both cars are write-off. For us, I mean, there's no middle ground. So both packets, both frames are gone.
We can resend. Yes,
we can resend. Yes. Well, first we need to know how can we recognize that this situation has happened. We can recognize this by two ways. Well, if we're talking about Sysma CD, we're lucky because, well, somebody out there will inform us, right? And somebody who detected the collision will have to inform everyone that there is a collision. But what if I did not receive this notification? Well, we have to use the same concept that TCP uses in that case, which means that I'm sending to someone, he did not send me back an acknowledgement, I will time out and I will resend it again. Okay, so the worst case is that I have to time out and resend it again.
Doctor, why the signals are not sent in different frequencies so they won't have any collision?
They could, but it's not the case for Ethernet. For Ethernet, it uses the whole bandwidth as one unit. It does not divide that because, well, if you want to send on different frequencies, then you have to divide your spectrum into ranges of frequency. So each range will be small. So you will not be able to send using the same speed on a shorter spectrum. So the problem with that is that you may assign this frequency range to someone and he's not utilizing it, right? So here it's in many cases more efficient because I make sure that whoever is trying to utilize, he will try everything, he will try the whole thing. So this allows one node to have higher activity than the other, and it utilizes the channel proportionally to the traffic that it has. If no one is utilizing the medium, then that's fine. I mean, the medium is there, but what I want to avoid is that I want to avoid the fact that I assign resources, I assign part of the spectrum, or assign the time to access the shared medium to someone. So even though others have data and they are waiting for him, but he's not utilizing the medium. So that's a waste.
Yes.
But if no one wants to send, then that's fine. I mean, I have nothing to send, so that's fine. So this is not a waste. The waste is that if you have something to send, but you cannot send because you want to wait for someone who is not trying to send anything. This is a big waste. Okay? So we'll stop here.